So now we're going to discuss the use of Koopman eigenfunctions as coordinates for, in this case, a linear system. So we're starting again with x dot is equal to ax. And A is a matrix, a constant n by n matrix. And so we're going to diagonalize A. And for each real lambda j is equal to sigma j, some real number here. So that's an eigenvalue, the jth eigenvalue. The coordinate yj can be defined as simply the eigenfunction. Remember, phi j was an inner product of x with wj, which is the dual eigenvector. And this eigenvalue, this eigenfunction then satisfies phi j dot is equal to sigma j phi j. In other words, this coordinate yj, which is really a function of the original variables x and a linear function at that, satisfies the equation yj dot is sigma j yj. So it's a simple equation. If sigma j is less than 0, then this, of course, when time goes to infinity, yj itself goes to 0 in an exponential fashion, with sigma j being the exponent. Now, if we have complex conjugate pair, lambda j and lambda j plus 1, which is lambda j complex conjugate, then we can use this complex linear transformation in the subspace that is spanned by a pair of complex eigenvectors vj and vj plus 1. And it's a simple exercise that from these new coordinates yj and yj plus 1, which are the real part of phi j and imaginary part of phi j, you obtain two equations for new coordinates yj and yj plus 1. And these two equations are given by yj dot and yj plus 1 dot being equal to this matrix here, that you might recognize from your vibrations class, multiplying yj and yj plus 1. So in the case when we have the complex conjugate pair of eigenvalues, we get this equation that should remind you of mass spring damper equations, where sigma j, if it's less than 0, would be the damping coefficient, and omega j would be the natural frequency. So in some sense, what you see is that anytime you have a linear system, and in this case we are considering simple eigenvalues, so not with algebraic multiplicity equal geometric multiplicity equal 1. You basically reduce the system to either one-dimensional components or two-dimensional components, and the one-dimensional components are simple dissipation. So going one-dimensional system goes to 0, and then two-dimensional components are really equivalent to a spring mass damper system with the damping coefficient sigma j and natural frequency omega j. Of course, you have to set up the initial conditions correctly. So yj of 0, according to this formula, is just the real part of your phi j. Since eigenvalues are complex, then the eigenfunctions are complex as well. So this would be phi, this initial condition would be a real part of phi j evaluated at x0. And then yj plus 1 at 0 would be imaginary part of phi j evaluated at x0. So we have a pair of initial conditions and two ordinary differential equations associated with each complex conjugate pair that has the same algebraic and geometric multiplicity. So now we can go a step further. So we could use polar coordinates in this plane defined as a span of eigenvectors vj and vj plus 1, this complex conjugate pair. so that that plane is spanned by the real part of Vj and imaginary part of Vj, or equivalently real part of Vj plus 1 and imaginary part of Vj plus 1. And so let's use polar coordinates on these, or in this plane. And then, then you obtain this transformation. Yj is Rj cosine theta j, and Yj plus 1 is Rj sine theta j. So our polar coordinates are Rj and theta j. And I'll notice immediately that that's a nonlinear transformation. And let's write our lambda j as E sigma j e to the I omega j. And then just starting from this set of equations, using this transformation, just taking a time derivative of Rj, we get Rj dot is sigma j Rj, and theta j dot is omega j. There's some computation required here, but it's the algebra is simple. And then the initial conditions are given by Rj of 0 there should be an absolute value, really. So it should be absolute value of phi j of x0. And then theta j of 0 is the angle of the phi. So argument of phi, of the polar representation of phi j evaluated at x0. So now, the linear system has these eigenvalues lambda j are sigma j plus I omega j, and its complex conjugate. What is interesting from these equations that we now got is that sigma j is also an eigenvalue of the Koopman operator, but it's associated with the eigenfunction Rj, or rather there is an eigenfunction Rj that's associated with it. But that Rj, if you take a square of this vector over here, that's equal to the square of yj. So yj squared plus yj plus 1 squared. And so it's a nonlinear function of the original coordinates. So we found an eigenfunction of the Koopman operator, but it's not linear, that eigenfunction. The same here is from this equation, theta j dot is omega j. You can look at e to the I theta j. Remember, theta j is, of course, a function of yj and yj plus 1 through this relationship. And so if you differentiate this e to the I theta j, you're going to get I omega j e to the I theta j. And so e to the I theta j is also an eigenfunction of the Koopman operator, but again, it's nonlinear. So that leads us to the question of, well, we started with these linear eigenfunctions, but there seem to be some nonlinear ones as well on a linear system. And we will see that those nonlinear eigenfunctions are also necessary for us to try to understand the behavior of observations, of measurements over a linear system, provided those measurements are nonlinear functions of state. So if we have observations and measurements that are nonlinear functions of state, then in order to describe their evolution in time, we cannot stick just with linear eigenfunctions. We have to include some nonlinear ones. And this gives you an example where such eigenfunctions, such nonlinear eigenfunctions are useful by themselves because they give us an interesting polar representation of the system that looks very simple. Part of it is a linear system. Rj is always bigger than 0, so it's a linear system on the right half of the real line. And then this theta j is an angle, so it evolves in a circle, and its evolution is a simple rotation using the quote unquote natural frequency omega j. So further, those new coordinates r1 and θ1 give us a semi-conjugacy. But while earlier we talked about linear semi-conjugacies, this one is provided to us by a nonlinear set of functions. And so it gives us a nonlinear semi-conjugacy. So take a map from your original state space to the positive real line cross-producted with S1. So this is a cylinder or half cylinder, right? Because it's just the positive real line. And that semi-conjugacy is given by m of x is equal to r1 of x e to the I θ1 of x. So if you define this map, it takes you from the original set of coordinates that lives in an n-dimensional space to a set of coordinates that are really defined on a cylinder, for which the evolution is given by this simple set of equations here. So rotation on a circle, and then also an associated dissipation towards 0 of this variable rj. So that's really a way of reducing our model again, our n-dimensional linear model, to a simpler system, but this time it's on the simpler system lives on a nonlinear object, while Rn, this space here, is a linear space, linear vector space. R1 and θ1 live on a cylinder, and that's a nonlinear space. So θ1s, so we talked about what functions like R1 or coordinates like R1 provide us with. So they give us isostables. So these are the absolute value of an eigenfunction, gives level sets of that, gives us isostables. Now θ1s are also important. They give you an object that is called, or partition into what is called isochrons, and we'll talk about isochrons in the nonlinear context even more. In this linear context, they are the level sets of the argument θ1 of this function over here. So from these types of analysis, we can now go to a slightly more general setting and say, okay, let's now dismiss the assumption that we have algebraic and geometric multiplicity the same. And in that case, as we know, we can have those generalized Koopman eigenfunctions that are still inner products between x and w. Just in this case, the w, j, I, is a dual eigenvector that corresponds to eigenvalue lambda j, but I is the index that counts the difference between the geometric multiplicity and algebraic multiplicity. For example, if algebraic multiplicity is mj and geometric multiplicity is just 1, then we go from 1 to mj, and in that particular case, when the number of dual eigenvectors, as you remember, the dual eigenvectors span the generalized subspace, invariant subspace in that case. The idea is to consider these, and we saw that eigenfunctions serve as nice coordinates for the system in the case of separate geometric and algebraic multiplicity. And here we are going to generalize that situation and say, okay, let's find a vector of these eigenfunctions. So this is a column vector that starts from phi1, 1, goes to phi1, m1. That's the multiplicity of eigenvalue 1. And you go from phi2, 1 to phi2, m2. and you end with phi S1. This S is the number of eigenvalues counted without multiplicities, to phi SMS. So S is the number of different eigenvalues. And then remember, we derived an equation for those phi kj's or jk's, so phi ji's in this case. So phi dot ij is lambda j phi ij. That part would be just like the ordinary eigenfunction equation. But then we had plus phi j I plus 1. So given this, the equation that this vector here satisfies is phi dot is equal to j phi, where j itself is a block diagonal, so-called complex Jordan form. So it's composed of blocks of a lambda j's and then zeros of the diagonal block. And a lambda j has lambdas. So for example, for the jth eigenvalue that has some multiplicity, some algebraic multiplicity, contains this block here. And then above that is this block of ones. The reason for that is this, right? So if you think about this whole thing as a column vector, you have phi ij multiplied with lambda j. That would be that for this first row. And then phi j I plus 1, in this case, I plus 1 would be phi j2. So that element would be sitting over here, and you need to multiply it by 1 to obtain this term. So phi j1 would be in the first row of that vector. And then you would have lambda j multiplying that. And then 1 is multiplying the next one down the line. That's how you get this. Of course, the lowest diagonal element is the eigenvalue itself. And then from this last row, you would get the eigenvalue equation for phi j mj. So for phi j mj, you would get phi j mj dot is equal to lambda j phi j mj without that term. That's just the equation for the eigenfunction itself. So that's the Jordan block, complex Jordan block corresponding to the eigenvalue lambda j. And so we have obtained the general representation of a linear system using the well-known Jordan block structure, but the way we got there was starting with generalized Koopman eigenfunctions. So that's different than the usual way we arrive at this particular conclusions. So it is the Koopman eigenfunctions themselves that provide you with the transformation to a Jordan block structure. Okay, so now we can work just a little bit more and try to get the real Jordan block structure. So we again use the polar transformation. So phi j is equal to rj e to the I theta j, and then theta j and theta j, phi j and phi j plus 1 get transformed into yj and yj plus 1, and we get the Jordan block that looks like this. So while the real Jordan block had eigenvalues on the diagonal, while the imaginary Jordan block had eigenvalues on the diagonal, the real Jordan block has these dissipation terms, if we wish to call them that way, provided sigma i's are less than 0, and then the frequency terms on off diagonal or off diagonal terms. And so here is a corollary of these considerations that says the following. Let's suppose that you have a set of functions phi. So that would be our column vector of eigenfunctions, for example, before. But let's suppose that we find a set of functions phi. Let's forget about a second, for a second about the notion of eigenfunctions. If these functions satisfy phi dot is j phi, where j is the complex Jordan normal form of a matrix, then that phi is actually a set of generalized eigenfunctions of your original system. And that particular corollary is going to be very useful for us when we consider the simplest form of let's say nonlinear systems that asymptotically converge to a fixed point from its basin of attraction. So let's say we have a basin of attraction with a fixed point, and it will turn out under appropriate conditions that we'll be able to transform that system, nonlinear system, ultimately to that form. And for that, we're going to use this kind of a result. So this is really kind of looking forward to what is going to be useful to us in the nonlinear case. But there is a nonlinear aspect on in the case of linear systems as well, and that nonlinear aspect is the issue of observations. So while your state X might be satisfying a linear equation, the observation itself does not need to. So if you remember, we had this situation where H, the vector of observables, was just some matrix C multiplying a state vector X. And in that case, it was enough to consider the principal eigenvalues of the operator. In other words, the eigenvalues of the system matrix and the associated, so we are also would consider the associated principal linear eigenfunctions. But when we have nonlinear systems, nonlinear observables, that will require a little bit more work. So let's start with an example. The idea is to study what happens when the observation that we have on the system is really not a linear function of the state, but it's some more general function. So the phenomena are easily seen on a simple example, and then we'll generalize away from that. So in this example, we have z dot is minus lambda z. Lambda is going to be positive for us here. So we have a stable system, and assume that our observation is nice in the sense that we can expand it, that observation u, so measurement u, we can expand in terms of the state z. So we can expand it as a sum from j is equal to 0 to infinity uj. So these are some coefficients, z to power j. If you remember, we proved earlier that z to the power j are eigenfunctions of the Koopman operator associated with this simple linear system. Uj is here because this is a Taylor expansion, is 1 over j factorial dju, so the j derivative of u with respect to z. And just to avoid any confusion, this is really not dz to the power j, this is the jth derivative of u with respect to z evaluated at 0. All right, so in the context of this observation, we are always going to be interested in its evolution over time, and the idea is to analyze that evolution by using spectral expansion. So if u Tz, which is by definition the action of the Koopman operator ut on u evaluated at z, so this utu is a new function that shows up at time t evaluated at state point z. So that can be represented by the following calculation. So utz is utuz. So that's action of the Koopman operator on u of z, which is this sum here. The Koopman operator is linear. It passes through this sum to act. This is a coefficient, so that's constant. So it acts on the function z to power j And we know that ut on z to power j is e to the minus j lambda t zj. If you look at one of the previous lectures, that's what we showed, that for this linear system, the monomial z to the power j is an eigenfunction of ut with the eigenvalue minus j lambda. So j is the counter here, or the power of the monomial itself. So that multiplies z to j. And that's interesting because pretty much immediately you can see that over a long time, the value of this observable at any z is just going to be the constant term that is obtained for j is equal to 0. For j is equal to 0, this is 1, and that's 1. So the limit when time goes to infinity is literally just u0, right? So the limit so that goes to u0 as time goes to infinity. And in fact, all these other terms, all these other terms from j is equal to 1 to infinity, they all exponentially decay to 0. Right? So that's a simple story about the evolution of an arbitrary nonlinear observable that possesses the property that it is analytic. And the other word for this particular property here that I'm asking for is it's actually entire. So it's a real analytic function that you can everywhere expand in its Taylor series. Yeah. So in order to achieve this description, we had to use eigenfunctions that are monomials. And so we have expanded the space of observables. So this whole space of observables or measurements that are not just linear, but also could be, finite or quote unquote infinite polynomials in the powers in Z, infinite polynomials in Z. All right. So now we are going to expand this story, and you will see that we are going to obtain a very similar and yet more general set of results. So we are going to consider a linear system in d dimensions. X dot is equal to ax. We're going to assume distinct eigenvalues, and we're going to assume an observable y is equal to f of x that is real analytic in X. So what that really means, what I'm asking for here is that I can expand the observable f in its Taylor series everywhere. So again, we are going to let the vector phi to be the vector of linear eigenfunctions of the Koopman operator. Note that I'm doing this for simplicity. I could have dealt with generalized eigenfunctions here as well, but just for simplicity, we are going to assume distinct eigenvalues. And these ones we are going to call the principal eigenfunctions. And the reason for this is that we are going to construct the other eigenfunctions from those using the property that the product of two of those eigenfunctions gives me another eigenfunction. And if I'm looking at analytic functions, that's going to allow me to do some expansions. So we're now going to consider the coordinate transformation that we just did in the previous part when we considered Koopman eigenfunctions as coordinates for linear systems. So we're going to say this vector of observables, phi of x, is a transformation from x variables to phi variables. But that transformation is nice and linear, and under the assumptions that we have non-degenerate, so we're going to immediately know that there is an inverse x of phi that exists. So there is a transformation from if I know functions phi, then I can get back the states x. So the next step, we are going to define the f tilde, a new function. That new function is going to be a function of phi, but we are going to do it by composing f with that inverse that we have just talked about. So compose f with x of phi, you get a function of phi, call it f tilde. So we started from an observation f. Now we have transformed that observation into to new variables phi that are provided to us by eigenfunctions. And one thing that we know right away is that the derivative of phi j is wj. How do we know that? Well, I'll just remind you that phi j is equal to the inner product of x and wj. So when you take a derivative of this, so d acting on phi j, of course, that takes out the x and leaves just the wj, right? So that's how we get that d phi j is wj, because phi j is a linear function, in fact, a complex inner product with wj itself. So wj is the derivative. And now we know that phi of x and x of phi are inverses of each other. So phi composed with x, evaluated at phi tilde, is phi tilde itself. So what we have is that this derivative of phi composed with x is identity, right? There is phi tilde here and phi tilde here. So if I take a derivative d of this at phi tilde, I get phi tilde back. So this is identity. And then by chain rule, you get the d phi I, the derivative of the ith eigenfunction, which remember is wi. That's this relationship here. So d phi j is wj, d phi I is wi. And then you multiply by djx. That's what this turns into. Identity in the index form is just delta ij. As the Kronecker delta, when I is equal to j, that is 1. And when I is different from j, that is 0. And delta goes obviously here from 1 to d, because we have a d-dimensional system to start with. And so here we have that so this. We have the wi. So that's this term here, times something is equal to delta ij. But we know the properties of the dual eigenvectors and eigenvectors, so this must be just vj, and we would usually represent this as an inner product earlier, right? So it must be that this term here is really just vj, the jth eigenvector, because this is wi. So when I inner product this with vj, that's when I get the Kronecker delta. All right, so we just proved that this derivative of x with respect to the jth eigenfunction variable. So this is a vector x. So the meaning of this notation is that each component of x, x1, x2, x3. So this is a vector, in this case the column vector of partial x with respect to phi, the jth eigenfunction coordinate. We just proved that that's the jth eigenvector itself. So far, so good. Because now we are going to take that, we're going to use this. We're first going to take this f tilde, and we're going to expand it into Taylor series in this coordinate phi. And so you can ask the question, well, is this globally possible? Because you could have some poles in this expansion, Taylor series expansion. Let's assume it is and proceed for a second. And we're going to get f tilde in coordinates phi 1 to phi d to be the following sum. So it's a bit of a gnarly sum, because it has all these components that go from n1 is 0 to infinity, n2 is 0 to infinity, to nd is 0 to infinity. These are all indices. In the one-dimensional case, I had only one index, so that was easy. But in the d-dimensional case, of course, I have d of these indices. But still, the Taylor series tells me, multivariable Taylor series in phi's tells me that I need to multiply phi 1 coordinate to power n1, that would be that index, with phi 2 and 2, phi d and d. I need to divide by factorials, n1 factorial to nd factorial. And then I need to take the n1 plus nd derivative of f tilde with respect to phi 1. So there are n1 derivatives in phi 1, and 2 derivatives in phi 2, and d derivatives in phi d. This is just a multivariable Taylor expansion in phi 1 and phi d as coordinates. And it's really an analog of this, where we have the factorial of g here, very simple, the j derivative of u. This all explodes into this this multiple sum, and then this derivative here is clearly evaluated at 0. This is where we chose to get our Taylor expansion at. So now that we have that expansion, we can apply the Koopman operator ut to it, and we know that for each eigenfunction phi j, the operator acts by multiplying phi j with e to the lambda jt. But so interestingly, in the Taylor expansion, we have these products of eigenfunctions, and the Koopman operator is linear. So when you apply it to f tilde, it passes through the sum, and then it acts on these individual eigenfunctions. But there are powers of eigenfunctions, right? So phi 1 to n1. And so ut acting on phi 1 n1. So let me actually combine this a little bit and say, if I put nj on top here, so that's nj, then I'm going to get e to the lambda jt to power nj, which just multiplies this lambda j here with nj. So that's how we get these terms, lambda j's, nj's. And then I have to put nj here. And then, of course, there is a sum, because you're acting on phi 1, phi 2, phi 1 on n1, phi 2 on n2, and so on to phi d on nd. There is a sum from j is equal 1 to d of those terms, lambda j, nj. And then we just copy this part over here. There is something interesting that came out, and that's this term here that tells you something about the evolution of your observable f tilde. Now, of course, we got this in terms of f tilde, which is our observable, as looked at as considered as a function of phi 1 to phi d. But if we wanted to consider it as the function of the state variables, the only thing that we really need to do is replace, or rather put back, what phi 1 depends on, and that's the state itself, x. And so now UTF, the original F observation, is this sum into the terms that contain the eigenvalues. And now you see that the eigenvalues here are the sums of original eigenvalues of the linear matrix. So these ones we call the principal eigenvalues, lambda 1 to lambda d, and they are multiplied by integers nj that are positive or 0. And that's quite interesting, because you're going to see that in a large class of systems, once you find these principal eigenvalues, for attractors more complex than just a fixed point, there is going to be more work to find those principal eigenvalues. But once you find them, then all of the other eigenvalues are actually generated from those. And therefore, despite the fact that that's a multiple times infinite sum, all of the information that you have in this sum is in fact obtained from d different objects. So here, d different eigenfunctions, and the powers are taken, and then d different eigenvalues and their associated sums over integers. The only thing that it's not is really these derivatives here, but as you remember, these are associated with the function itself, not with the operator. But this term here and that term, you will know without computing an infinite number of objects. So it's really a finite, again, still a finite dimensional computation to obtain those, because you really need the first d, and then the rest of them are generated by those objects. And so this is what is called the spectral expansion formula. And for the first time here, we are seeing it for a nonlinear context. So we had a linear system, but we took nonlinear observables on a linear system, and we obtained a spectral expansion formula in terms of eigenvalues, eigenfunctions, and modes. So these things here are Koopman modes that were just eigenvectors in the past. So let's look at them a little bit further. So in the previous case, we had a scalar function. So a Koopman mode would be itself just a scalar. But if we have a vector valued function f from Rd to Rm, so for example, in a physical situation, this could be a velocity field of a fluid evaluated at each point. You have many observables that are associated with various physical points in the field. Then the evolution of f, so boldface f under the Koopman operator ut, is pretty much the same as before, except that this derivative now contains our f tilde as a function of phi 1 to phi d. And so if you label this by the indices, this term by the indices, and name it v of n1 to nd, then this derivative here, which is a constant vector because it's evaluated at 0, and 0 is my fixed point of a linear system, that is our Koopman mode. We can index it saying that is the n1 to nd Koopman mode for the evolution of f under e to the at. And so it's interesting to look at these Koopman modes and say, okay, physically, what do we get out of this? So if we had a linear observation, then we actually got the Koopman modes were eigenvectors if your observable was the state, full state, or they would be some matrices acting on eigenvectors if the observation was not full state but was a linear function of state. In this case, okay, let's select for n1 to nd all zeros. If we have all zeros, then that is the zeroth, quote unquote, zeroth derivative of f tilde. So it's just the value of f tilde at 0. So the 0, 0, 0, 0 mode is really just the value that of the observation that the system gets asymptotically, precisely at the equilibrium point. And we will see that that's a very general story. So Koopman mode associated with the asymptotic, one of the Koopman modes associated with this asymptotic evolution to the attractor is the time average of the observation under the evolution. This is going to be quite a general theme for nonlinear systems. Here you see it by the fact that when time goes to infinity, you're going to observe f precisely at 0 because the system, in the case of stable system, because the system goes to 0, right? So all the lambda j's, I'm assuming that all the lambda j's have negative real parts in this case. If we get, instead of 0, 0, 0, if we put 1, 1 among all those, so at the jth position of this index, we put a 1. Then we're going to get df of 0, djx of 0. And this, I proved previously, is just vj, the eigenvector itself, right? So we have a function f of x. So when we differentiate that once, we get df evaluated at 0, djx evaluated at 0. That dj is the derivative of the vector x with respect to phi's. So that's how it comes from this formula. And so you get df of 0, and then djx, we showed earlier, somewhere here, that djx is just vj. So that's interesting again, because this Koopman mode is really the eigenvector of the linearization of the system multiplied by df. So if f itself was the state x, this would be just identity, and you would get the eigenvector of the linearization again. And that makes hopefully a lot of physical sense. So the 0th term is what you observe at the fixed point. The order 1 terms are all modulations. The Koopman modes associated with order 1 terms are all modulations of the individual eigenvector, modulated to the fact that you might be observing something that is not a state. If you're observing something that's a state, then you get immediately back the eigenvector. And so in this case, the dynamics of the system was linear, but the observation was nonlinear. And so we needed a full set of eigenfunctions of the Koopman operator, a full set in the sense that I was assuming that the observable is analytic in the eigenfunction variables itself, phi. And I needed many additional eigenfunctions on top of the principal ones, but I could obtain these additional eigenfunctions by multiplying them with themselves or with the other eigenfunctions. And so I got all of these expansion terms from the algebraic structure of the eigenfunctions themselves. So 2 eigenfunctions if I have two eigenfunctions, then the product is again an eigenfunction, provided that that product lives in the same space as the original eigenfunctions do, and in this case, that is true. All right, so just to finish this lecture, a few papers. The first paper in which this was studied, I believe, is this one over here in General Fluid Mechanics. And the full theory was for the first time presented in here. In fact, much earlier in my set of lecture notes. So there are a number of students at University of California, Santa Barbara that have seen these results before. They were published in this paper. There are some earlier works by Gaspard and collaborators that considered it in some restricted context. And then the isostables, the concept of isostable itself was developed in this paper 10 here for the first time. It was named in that paper. And as I said, what is interesting about it is that it's the first geometrical concept in dynamical systems that strictly comes from considerations using Koopman operator theory. I will talk about isochrons a little bit later on in more detail, but those geometric objects had a precedent in geometric analysis of dynamical systems. The concept of isostables really didn't. Okay, we'll stop there, and next time we are going to start the analysis of a class of nonlinear systems, in particular those that are stable within that have equilibria that are stable within a basin of attraction.